Okay, so let's say that we have an infinitely long current carrying wire. It looks like that, and it carries current, let's say I naught to the right. All right, so it's a uniform current to the right, and we have a charged particle of charge, let's say Q star, that is launched with a speed v naught, let's say, into the board. So the speed charged particle is right here, and it has a speed which is at the back of the arrow, right? So that represents the velocity, and it's at a distance, let's say, a distance d from the wire, the infinitely long wire, and we want the magnetic force on the particle, which of course is the QV cross B. And so we need to evaluate these quantities. So a particle of charge Q with a velocity V in a magnetic field feels a magnetic force. So we know what the velocity is. It has magnitude V naught and direction into the page. The magnetic field, we need the magnetic field at the location of the charged particle, and so that's going to be determined by the current, right? So magnetic fields are determined by the Biot-Savart law. Okay, so I've written the DLs here as DRs before, but they are just little pieces of the wire with DL. All right, so they carry the direction of the current, but they involve, these are tiny, infinitesimally small distances. Okay, so every little piece of the wire produces a magnetic field, a tiny magnetic field contribution at the location of where the particle is, and we have to add all of those up. That's what the Biot-Savart law says. So this allows us to get the direction of the field here, given all of these current elements. And if we wanted the magnitude, we could find the magnitude with this as well, but it's easier to use Ampere's law. But it turns out that in this case, we don't need to find the magnitude simply because the magnetic field at this location, right, given by the right-hand rule applied to this part. Okay, so to find the direction part of B, we need that, and so all of these DLs, if we go all the way back to infinity on the left, all the DLs are pointing that way. So we have the index finger describes this, DL, and the middle finger needs to be pointing towards this location. So although I have to bend my middle finger something like that, and the further back I go, the more the middle finger approaches the index finger, but the result is always the same. Right, just like the easiest way to do this is to look at a current element right there, put the index finger there, and then the middle finger toward the position of the particle, and the thumb tells us the direction of the field. And that's always the same, because even though the angle's changing, right, when I go from minus infinity to plus infinity, the angle between the middle finger increases all the way by 180 degrees, the result is always the same, that the magnetic field, which I'll make in blue, is into the page as well. So B, by the right-hand rule applied to this part of the Biot-Savart law, tells us that the magnetic field is pointing in. So velocity and magnetic field are aligned, and so this goes to zero. So the magnetic force is zero. I don't need to evaluate the magnitude of the field. But let's say that instead of launching it into the page, the particle is launched, So we launch the particle with a speed v naught to the right. Okay, so the velocity is to the right. In this case, what we have is a non-zero force. In fact, we have the maximum force because the magnetic field is into the page and the velocity is to the right. So there's 90 degrees between velocity and magnetic field, and therefore the force will be the magnitude times some unit vector, and that will not the force will not be zero. So we need to find the magnitude of the magnetic field. So the first thing to notice is that let's see, we could write, we don't have coordinates here, so let's find the magnitude separately and then separately point out the direction. But the direction of the field, of the force, will have to be the result of the cross product between V and B. So V is into the page, so my index finger is pointing into the page, and I changed it. V is, the velocity is to the right, so the index finger is pointing to the right, and B is into the page, and so the thumb points toward the wire. So in this case, we would say the force is toward the wire. Of course, that's only at that exact location. As soon as the force starts to change the direction of the velocity, then the direction of the force also changes, right? The conditions for circular motion apply, and the motion can be kind of complicated, but right at that position, the force is toward the wire, and now we need to find the magnitude. So what's the magnitude of the magnetic force? Well, it's the magnitude of the charge, which is Q star, times the magnitude of the velocity, which is V naught, times the magnitude of the magnetic field, which we don't have, which we have to find, because we're given the current, times the sine of the angle. But the angle between velocity and magnetic field is 90 degrees, and the sine of 90 is 1, so it's just 1 there. So we have to find the magnitude of the magnetic field at a distance d below the wire. So if we look at the wire, at the current configuration from this perspective, right, the wire is coming straight at us, so it looks to us like this, right? Then the position of the particle is a distance d below the wire. The particle would be here, and so this is the distance d below the wire, and we need the field there, and so of course Ampere's law applies here. If we can find a path, let's make a red path that goes to the point where we want the field, where everywhere the field is expected to have the same magnitude. Of course, that's a circle, right? So I'm trying to make a circumference here of radius d and apply Ampere's law to that. So Ampere's law says that the integral of the magnetic field over some closed loop is equal to mu naught times the current enclosed. And so the left-hand side of this, given the path, the red path that I chose, will reduce to the magnitude, which is the same everywhere, times the length, which is 2 pi d, and the right-hand side is mu naught times the current that's enclosed. This goes through the area that has the red path as the boundary. That's just I naught. So the magnitude of the field is mu naught I naught over 2 pi d. And so we now can write this as Q star V naught times mu naught I naught over 2 pi d. So that's the magnitude of the force at that location, and the force direction is toward the wire.